This lecture is about text. And when I said to someone yesterday, I'm giving a lecture about text, they automatically assumed that I would be talking about the short message service that we have on our mobile phones. And they said, how on earth? Firstly, they said, oh, computer science, how boring. And I thought that was hardly a rave review. And then they said, oh, text, well, what can you possibly say about text that hasn't already been said? Actually, I don't want to talk about the short message service. I thought it is an example, though, of how text is so persistently used by us humans. We love the stuff. You know, we use it for communication. It's the favoured form of communication for intelligent people, text. And it's not entirely obvious why text is quite so popular. So I thought I would start by just observing that actually the earliest computers were not intimately coupled with text. This is Univac, which is, well, people will dispute about the history of computing, don't they? But this was probably the first commercial computer. And as far as I can tell, I'm not an expert on the history of technology, but I did scour the libraries for photographs of every early computer I could find. And this was the first one to have a QWERTY keyboard on it. Here it is. Doesn't it look marvellous? This is the operator's console of Univac. I have a real feeling I would like a Univac in my briefcase. You know, it looks very impressive, and I love the little meter up here and the valve heaters down here. It doesn't yet have a display unit, or a VDU, as we used to call it, a visual display unit. And the reason was, of course, early computers were generally programmed using punch cards or taped or punch tape, and the keyboard, if it was used at all, was used to to make alterations to the programming device. It wasn't used to directly communicate with the computer. And what happens, of course, in the early keyboards was, it isn't obvious here, but there would be 8 wires, or maybe even fewer, that ran out of this keyboard. And as I pressed a particular key, I would set a pattern of 0s and 1s on those wires. And that's called a code or a map. Okay, it sort of maps the characters into some sort of digital code. So if we took some example text, and this is just a little bit of text I copied from Wikipedia, at a low level, what we would see for each one of these characters is a binary digit, or because it's a bit boring to write binary, we'll often write it as decimal or hexadecimal or something like that. So the code that was commonly used in my youth was known as the ASCII code, the American Standard Code for Information Interchange, is what it stands for, and each letter is given a binary equivalent, and I could have converted that binary into decimal or hexadecimal. Most of us remembered the hex, so I is 49, N is 6E. Everyone remembers space, which is decimal 32, and hex 20, and so on and so on and so on. So that's the coding system of the past. And of course it led to one of the best jokes on the planet. This is a joke that can only be understood by British computer scientists who are over the age of 50, which is a narrower set of people. And the joke is, Arthur ASCII, what a character. Yes, there's a group, for those of you who are online, there's a group in the audience who I'm sure don't mind me saying are of a certain age to know who Arthur ASCII is. Arthur ASCII was a sort of character comedian from the early years of British comedy, and he was a bit of a character. And of course you have to know what ASCII means. Anyway, let's not explain jokes to people, but it is one of the most niche jokes that one can make. When I told my friend Andy Stanford-Clark, who is the technical director of IBM UK, that joke, he's my age, he thought it was hilarious, and I had to pick him off the floor. I told my wife, and she didn't get it at all. So fair enough, that's because my wife's too young. Now, in the real world, of course, it's probably worth saying that if you were working in computers when I was a kid, effectively you had to learn American, because it was the American standard code for information interchange, and it had, the American alphabet, which as we all know, is almost identical to the British alphabet. But it certainly wasn't very international. Now, this is the first, I think I did about 2,000, first 2,000 characters from Unicode, which is the current standard for character mapping. This is Unicode 12.0, which represents around 140,000 characters across a large number of languages. Not all languages are coded, but it's a pretty impressive attempt to try and code a lot of the world's languages. It is not without controversy, actually. Very early on in Unicode's history, there was an attempt to deal with Chinese, Japanese, Korean, and to some extent Vietnamese characters, all of which, as I'm sure you know, are stroke-based. So the observation was, well, a lot of these characters share strokes, so we can share some of the codes in order to encode them. That proved to be somewhat explosive, and there is still a little bit of, well, not a little bit, there's some mudslinging and some debate about the decisions that were made early on in Unicode. For those of you who are interested and can read Japanese, I'd recommend a technical memo on the matter from the Japanese computer manufacturers, which has a wonderful title, which is translated for us in Wikipedia as "We are feeling anxious for the future character encoding systems." Well, you know, that is another one of them. That's wins the prize for the world's most niche title, doesn't it? So also surprising to see that the aggravation is coming from Japanese scholars. And their observation is there are quite a few old characters in Japan which aren't properly coded by Unicode. Right then. Okay, all of which was one of Richard's little diversions. I want to get back to this business of code equaling characters equaling numbers. So these codes are flowing through the system, and they're being pumped through computer systems like blood, systolically. So what could we do with these characters? Well, the simplest thing, and I talked about this in my first lecture when I was talking about information, is just to count them. So this is a count of all of the characters in the British language. Here are the characters along here. I've ignored the upper and lower case, and I've ignored punctuation. And this is the frequency of those characters. Blue is English. So looking at the most common character in English, which is E, we get the immortal phrase, which everyone knows, and everyone in this audience knows because it was mentioned in the first lecture, Etuain Schlurdlu. Etuain Schlurdlu. Everyone knows that Etuain Schlurdlu is the order of English characters by their frequency. ETOANSHRDLU. Okay. Now, and in red here is another language. Can anyone guess what that language is? It's a language that shares most of the characters with English, although it does have a few of its own. Yes, absolutely right. The person who cried out French has done an excellent job. Okay, and the clue is here. Okay, there's a very big difference in H use in the English language from French speakers. French speakers are not very enthusiastic about the letter H, as we all know. So that's a clue to one of the uses for unigrams, which I shall come back to in a moment. Well, unigrams is a sort of technical word for single characters, and if we were to measure pairs of characters, we'd usually call those bigrams, character bigrams, okay? And these are the character bigrams in the English language. So TH, HE, ER, and so on. When you look at these are the very common suffixes and prefixes that you find in the English language. Is it obvious? But perhaps it's not obvious. Let me just say it. The frequency of these things is considerably lower than those of the unigrams. And there's a reason for that, and that's because there's just a hell of a lot more of these things. So this was realised quite early, actually, this idea that these unigrams, bigrams, trigrams, quadgrams, if you prefer the general Ngrams. Okay, an Ngram is just a combination of n of these characters. This was realised quite early on in the history of computer science that these things were likely to be quite interesting. And one of my favourite papers on this comes from 1994. It's by Bill Kavanagh and John Trenkle. And what they did was rather cunning. They measured the frequency of all of the Ngrams in documents. So I think here they probably were looking at the first 100,000 characters. So they're measuring frequency here in absolute terms. And perhaps it's not so obvious. I've copied the paper direct. In the interest of authenticity, I've copied the diagram straight from their paper. Perhaps I should have done my own. But there's this very steep decline here. Now this shape here, which is very common in information retrieval and library science, is known as Zipf's law, Z-I-P-F. And Zipf's law has this steep curve, and the probability is inversely proportional to the rank of the thing down here. Now what they observed was that when we look at this here, these first few characters, they are the Unigrams, so they are the most common things. And then the next most common thing down here, they're the Ngrams. They usually consist of function words and common prefixes and suffixes. And broadly speaking, they say the first 300 of these depend on the language that's being used. And then down here, we get dependency on the domain, what the document is about, the author, and so on. And that's how you spell Zipf's law. Zipf's law comes up a lot. It's very, very common in these things, and it's just an experimental observation. It doesn't have much of a theoretical basis at the moment. Okay, so if you want to build a language identification system, what you do, they say, is you just select the first 300 of these, and they give a nice little algorithm for selecting these things. It's quite easy to build, and you build a little signature, you compare them, and off you do the language identification. And if you're using a language ID system at the moment, and you probably are if you type in some German or Hungarian into the web and it automatically adjusts its language, then it's almost certainly using this system. It works really well. Now, there is a problem with this method, the Ngram method, though, and it's called the Curse of Dimensionality. And the problem works like this. Let's say we had 26 letters. Well, you can imagine implementing that. 26 counts is fairly easy to implement. So we get some text and we go through it and we count each one of these letters. And because there's only 26 of them, let's say, 21 if it's French, but it's a small number, we can easily just rattle through and get a count. And we don't need that much text to get a count. Cool. So that's why unigrams are used for text. As soon as we've got bigrams, we don't just have 26 counts, we've got 26 times 26 counts, so that's 676 counts. And if we have trigrams, we've got 26 cubed counts, 17,000 counts, and 26 to the 4 is 500,000. So you can see the problem. The data structure that you're using to store this gets big very quickly. Now, 500,000, whatever, 500,000, who cares about 500,000? That's not very big, and I can fit that on my mobile phone. The issue is, because it's a histogram, there's a general rule of thumb that probably for every bin you need 10 data points. So if we've got to fill 500,000 entries in a histogram, then we're going to need 5 million characters. And how many characters to a page? About 2,500, isn't it? So every 2 pages you've got 5. So you need 2,000 pages of closely written text in order to build the data you need for just a quadgram, which isn't very much. A quadgram doesn't even capture lots of words. And so this problem comes up a lot in computer science, the curse of dimensionality. And it's a twinfold curse. One is the data structure's a bit big, and the second thing, it takes a lot of things to fill it. However, I have introduced something that is potentially quite handy, which is I have sort of converted this great big lump of text, pages of text, into, in this case, only 26 numbers, or in this case, 676 numbers, in this case 17,000 numbers and so on. So what I've been talking about already can be thought of as a mapping, really. So I'm moving from a piece of text through to a fixed set of numbers. Okay, and we would call this a feature vector, normally. It's just so if it was the Unigrams, these would be 26 counts that represent, say, the letter frequencies in this bit of text over here. Now, in the previous lecture, we were talking about deep learning and a type of artificial intelligence called pattern recognition. And what I said in that lecture, it doesn't matter if you weren't there, but the essence of the lecture was, if you can get your problem into this form, then we can learn the relationship between this and some sort of class, some sort of output. So this is potentially helpful when thinking about modern text systems. They've essentially got two stages. One is text to feature, and the next stage is feature to class or problem solution. That last bit, feature to class, that's AI, right? I'm just going to put that in a big black box for the time being and say, that's machine learning, already discussed, many algorithms for doing that. Now, that might seem a bit primitive, but that, ladies and gentlemen, that was the 10-minute version of the whole of the text processing information retrieval class, okay? If you can get some number that represents this, then you just boot it down the road to a machine learning thing and you're sorted. Right then, what are the choices for that number? Well, we talked about these. Ngrams are an example of something called a bag of words model. Unigrams are perhaps the easiest one to think about, but I've been up to this point I was talking about unigrams for characters, for individual characters, but we could also have unigrams of words, so we'll just count the number of words. A slight problem with this, English in particular has quite a few, and Greek, to take another one, that has quite a lot of words to choose from, so we might have to throw some away, might have to restrict the set. And the bag of words model, which you'll hear sort of bandied around in trendy machine learning circles, is essentially a word count. Okay, so I killed Robin, for example, is treated identically to Robin killed I in the vast majority of machine learning systems that use bag of words model. So already I can see you sort of recoiling at the simplicity of this, because I killed Robin most definitely doesn't mean the same thing as Robin killed I, even if Robin killed I was grammatical. Right? It certainly has another meaning, but for any bag of words model, and they're very common at the moment in machine learning, then they do mean the same thing. They are just counts. Okay, so that's a little bit of a buzzword, really, the bag of words model. What I'd like to do is just quickly tell you, though, about two others. These are two ways of trying to convert text into this list of numbers. So they're text to vectors. And I'm going to tell you about one that is a sort of bit of a historical curiosity but doesn't really work. That's called latent semantic analysis, but it's quite neat and it comes up a lot in the literature, so I thought I'd talk about it. And then I'm going to talk about one that really does work and is used very extensively in modern systems. I should say in computer science, modern, by that I mean Word2Vec, probably dates from 2013, right? So it's very unusual in computer science to be very interested in anything that's older than 10 years. If you graduate students frequently say, I've been reading this paper, and the first thing you do is look at the date on the bottom, and if it's older than 10 years old, you say, it's rubbish. To a first approximation, it will be tat. But LSA is quite instructive, and it is a bit antique, so I'm going to talk about it, partly because I'm antique, and partly because it's kind of an interesting little diversion, and it has an interesting history. So latent semantic analysis, or LSA, has interesting history. It was really thought of by an American psychologist called George Kelly. And Kelly was around when, I don't know if you remember, but psychotherapists in the old days, I'm sure they don't do this now, used to sort of declare which tradition they were from. So they would say, well, I'm a Jungian psychotherapist. Oh, I'm a Freudian, And Kelly found this rather annoying, because it would mean that a person who had some sort of condition got a different description of that condition depending on who was talking to them. It was most peculiar. It was like using a ruler to measure something, except the ruler was made of rubber, and so depending on who was using the ruler, you got a different answer. And he thought, well, this can't be right. There must be some inner truth or personal construct, which is what the patient is feeling. And my job is to try and reveal what that personal construct is by looking at these multiple answers that I've got from the various analysts. So he devised a technique based on a mathematical technique called singular value decomposition. And this has now become known as LSA, and here's the key paper on LSA. I can explain it really fast, though. So let's imagine we've got some documents. And I've just picked this example because it's one of the classic examples in LSA. They're all documents taken from mathematics, as it happens. They're papers in mathematics. And if you know anything about mathematics, you can see there's two sorts of papers there. There are papers about, let's pick one. There's papers about partial differential equations. This one is, paper B4. And there's papers about algorithms. Okay, Hamiltonian dynamic system, n-body problems, and so on. Okay, and just for simplicity, we're only going to consider the underlined words here. The authors of this paper are throwing away some words. This is very common, by the way, and I'll say a little bit about this later on. The principled or unprincipled throwing away of data is extremely common in text processing, and you may well wish to ask yourself a little bit about it. How did they throw that information away? So one of the first things you could do is you could represent these list of documents as a matrix called a term document matrix. So these are the underlined words. They're called the terms. Search people refer to search terms. And these are the names of the documents. So, for example, this says that the word algorithms appears in document B3. Thank goodness it does, right? So we can look at this. Now, this is a raw count of the number of times things appear in a document, and in this example they only appear once, but of course they could appear multiple times. If we had a paper that was called equations, we would get a count of 5. Did I do equations 5 times? You know what I mean. Anyway, this matrix is the basis of retrieval when we're talking about internet retrieval, the business of Google or text retrieval. People are generally imagining this great big matrix here. You could think of these as web pages, and these are words contained on the web pages. So the trick of the LSA is to approximate this matrix in some way. However, I should just point out that you might work on this matrix, which we're working on here, which is the raw count, as it might be called, but we would probably do some pre-processing in order to make it a little bit easier. Now, I say probably because if I was giving this lecture maybe 4 or 5 years ago, I would have said, we definitely do some pre-processing. But things are on the move a bit in text processing, so some of these standard things that we do probably aren't worth doing anymore, and in fact may be hurtful. But let's talk about some of them. So the first one, we've seen this already. I decided at the beginning of this example just to arbitrarily throw away some words. Now, we did it because we didn't want the matrix to get too big. But this happens all the time. And the words you throw away are usually called stop words. And they're called stop words because they stop your system working. Okay? Now, words like the, is, on, at, those sorts of words, they appear everywhere. So you say, well, let's not bother counting the number of times at appears in anything. Let's not strike it out. So if you're interested, on the transcript, you can find a little reference that will take you to a list of stop words in a variety of languages. They are completely arbitrary. I think I will stick with that. They are in the minds of a designer. Somebody says, I'm not interested in those words, they won't be useful, strike them out. Well, obviously they depend on the designer, they depend on the domain, and all of that makes you feel a bit sort of creeped out, and we don't like arbitrary and whimsical things. So stop words are common. The other thing that might happen is that words are merged on the basis of their stem, so their morphological root. So let's think of an example. Fish, fishing, fished, fisher would all be converted to the word fish. Now you might protest that a fished and fisher are not the same thing at all, and they're not. Okay, it's another big approximation that's made in a lot of conventional text processing systems, but you've just got to narrow the space down a bit. So stemming is common, and you can download and use the standard stemmer, which is called the Porter stemmer, if you like, and use it. Again, nowadays, telling people about stemming is a sort of lovely thing to do in undergraduate courses on information retrieval, because you can absorb an hour and a half telling people about stemming algorithms. And by the way, if you're teaching in Hebrew or Arabic, then you could probably absorb 3 hours, because it's much more complicated stemming those languages than it is humble old English. But I suspect nowadays it's not worth doing. We'll just let the artificial intelligence speak about it. What is worth doing, and what is commonplace, is not to use the raw count, but to divide not only by the number of times that term appears in all documents, but also work out how informational that term is, and to normalise by that. So when I say informational, I'm using the Shannon information, which we sort of talked about a little in the first lecture of this series. All of which allows us to approximate this thing on the left, which is a visualisation of that matrix, with something over here. And the important thing about this approximation, you either know how singular value decomposition works, in which case those of you in the audience who know are feeling smug and full of yourselves, good for you, or you don't need to know. What you have to know is I can use just 2 dimensions to approximate this thing. So there are 2 little vectors, and with a little bit of fancy multiplication, I can recreate this approximate version of it. So I can visualise those things on a little graph like this. And I don't know if you can see this, but there's a sort of cluster over here, which are to do with differential equations, and there's a sort of distance over here that's to do with algorithms. Remember, we had 2 sorts of documents in my original. One was to do with algorithms, and they're all down here, and these words are all up here. So this allows you to sort of express concepts in terms of linear combinations of words. It's a bit like, expressing, you say, well, what is rage? And you say, oh, well, rage is 50% anger and 50% 20% foot stamping and 30% flushing and 20% flushing and 10% fist shaking. That's exactly what LSA allows you to do. It allows you to put numbers against these percentages. So, of course, when you get some new document, what you can do is just project it against these concepts and work out where it sits in the space. So if you're going to go and do some machine learning, this is terribly handy and useful. That said, LSA really has failed to deliver, in my opinion. I mean, it's very commonly talked about in undergraduate courses, but it's really too simple in order to be useful to us. The concept is useful, which is this vector space, and in this space of numbers we have these concepts, but the mapping it provides is really a bit too primitive. However, help is at hand, and in roughly 2013, somebody introduced a new mapping, which has had a big impact on the field, and that mapping is called word-to-vec. And I'll talk a little bit about it in a moment, but I thought I'd start by showing you some of the cool things you can do with word-to-vec. And this is some nice work it's a nice blog, actually, by someone called Casper Berlin, who I don't know, but I'm admiring of the blog. What they did was they took all of the statements from female MPs in the House of Commons from 1945 to 2014. Now, this is a sort of standard thing to do in social sciences and humanities, and you can see it's a bit of a problem. What you'd like to do is you'd like to look at all of this text and to come to some conclusions about how female lawmakers, if that's what you're interested in, and that's what this person is interested in, are expressing things. Well, you can imagine, you can imagine the debate you have over that. You'd sort of make a list of the words, and then you'd have to deal with the synonyms, and then you would have to argue whether the fact somebody uses a word a lot means anything. We've just seen that argument, the stop words, what are they doing there, and so on and so on and so on. So what this person did was they mapped them into a nice little space, and they've managed to produce this graph. Each one of these represents a word, and each one of these lines is an indication of closeness. So I've zoomed up one part of the graph here, and you can see here are some of the concepts that have been discussed by female MPs. I think this is fairly recently, actually. Now, a couple of things to observe. Some of the words in this graph were never used by female MPs, I'm pretty sure. Right? I'm fairly sure about that because no one in the United Kingdom uses the word math to describe mathematics. Right? We call it maths. Right? Maybe illogical to call it maths, but we don't use the word math. So what the hell is this doing here? Well, they probably used a pre-trained network, which was probably trained using an American text. So what's happened here is you've got this retraining stuff that's overlaid on top of the existing training, which is very helpful. They can also then split this into concepts. So what this person has done is they've interested in the concepts that have been important by female MPs over the ages. And I'm not sure how scientific this is, and I'm not sure that this has actually been peer-reviewed, but it caught my attention because it's quite dramatic. So these are the concept clusters, okay? So from the period 1945 to 65, they found these 3 clusters of important discourse by female MPs. And you can see what they're about. They're about, what's the first one about? Cleaning, really. And then this is about foodstuffs, isn't it? And this is about sort of commodities. And I assume what's happened here is we're just coming out of post-war rationing. So these are quite sort of consumptive concepts. And then these are the concepts in this period, the 1960s through to almost the current day. We've got transport, sexual harassment and or violence, and politics of reproduction. Now, what I like about this really is that the concepts have emerged from the data without too much debate amongst people about a lot of sort of minor semantics about the words. Really rather nice bit of text processing. And I thought I'd start with this because it's one of the more interesting applications. Of course, there are a great number of mundane applications, and one that sprung to mind, partly as a result from the last lecture, was the problem of fake reviews. I don't know if you noticed, but Which magazine is currently pointing out how superior it is as Which magazine is a British consumer magazine, and it is fond of pointing out that it's extremely superior methodology for comparing products because it doesn't rely on reviews. So the spotting of fake reviews on TripAdvisor, Yelp and various other places has become a standard problem in artificial intelligence, made a lot easier by Yelp, I think it was Yelp, collecting a vast number of both genuine and fake reviews. So they used sort of intelligent sources to gather fake reviews. You can spot some fake reviews by the fact that, if 1,000 reviews all appear from one IP address in a space of 10 minutes, they're probably fake, So this has proved a really useful source of stuff for machine learning. And in fact, I'm sure you can just go online now and tell whether reviews are genuine or not. This is one of my favourite websites that does this. This is FakeSpot. Anyone used FakeSpot? Oh, it's great. It's always good fun. This is I picked this because this was the hotel I was staying last week, and I thought, I will just check some of these suspiciously positive reviews about this hotel. I'm happy to tell you that the Ibis in Riyadh has an A rating, no fake reviews there then. And what it's done is it's gone through all of these reviews and it's classified them as true or fake on the basis of a set of rules. And like with all deep learning, I'm not entirely sure what those rules are. One of the clues for fake reviews, by the way, if you're interested, is lack of detail. Okay, fake reviews are often, say this place is amazing or very bad. fake reviews are becoming a bit of a problem because of this problem called crowd turfing. So crowd turfing is where I pay someone $3 to write either a very nasty fake review about one of my competitors or a most excellent review about myself, and it's sort of ruining the review space. I'll come back to it in a moment. Right, now, what about this word-to-vec mapping that I was talking about? Well, word-to-vec mapping, it uses a form of deep learning called a bottleneck, and I talked about bottleneck learning in the last lecture, but the idea is really quite a simple one. What we're going to do is we're going to take maybe 5 words in sequence, and they're going to form the input to our network. And I'm going to so plus or minus 2 words around a word. And then the network architecture is going to go to this narrow part here, maybe 1,000 numbers here, and then I'm going to learn out again to relearn those words on the output. So this is a funny looking network. It's a network that's trying to learn its input with the missing word in the center. The advantage of this is we're not interested in the output. The output is just a learnt version of the input. What we're interested in is 1,000 numbers in the middle. And that's the internal representation that the network is being forced to use in order to solve this problem. So that's a vector. So what we're essentially doing is we're asking a neural network to learn itself, learn its input, and then we look at the internal representation the neural network is using and say, that is a vector. It's a sort of, that was totally non-transparent in the sense, it's not at all obvious. You can't just look at these numbers and know what they mean. You have to have the inputs there in order to give them some sort of semantic meaning. But it's bottleneck learning. And word2vec has been remarkably successful at doing this problem. It was dreamt up by a Czech researcher who I suspect was frustrated by the complexities of the Czech language and the sort of mangling it got in a lot of search engines. And the task he set himself was, he said, well, what I want to do is let's think of this word2vec system as a mapping. So if I put in the word France, I'm going to get a number out in my 1,000-dimensional space. So I say France, and this little number comes out here, which I'll represent in my sort of 2-dimensional space around my head. So that's France. And he says, right, now let's say Paris. Okay, well, Paris is over here. And then he does something really quite dramatic. He said, well, there's a distance between France and Paris in this space. Now then, where does Rome appear? And he says, well, Rome's over here. And he says, oh, okay. Sorry, where does Italy appear? Italy's over here. Right, let's move this vector over here. Where does that point? It should point to Rome. It does. So when this happened, this was really very, very dramatic discovery. You've discovered a space in which the vector for France minus the vector for Paris plus the vector for Italy equals Rome. So this is an example of him doing this problem. So he says here, well, if Paris is to France, then if I put in Italy, my network should output Rome, which it does. And if I put in Japan, it should output Tokyo. If I input Florida, it should output Tallahassee, and so on and so on and so on. Now, are they all correct? I'm just looking for one that might be wrong. Oh, little tinkery, I think he's picked them all right, hasn't he? Yeah, so neat. There we go. An error at last. Whew. Where are we? Google, Yahoo? Here? Yeah, you're right. Thank God. Right. Okay. So Steve Ballmer was the chief executive of Microsoft. Jobs was the chief executive of Apple. I can't remember them. Was it Bill McNeely? But Yahoo is not a person. So there are errors. Okay. But this was a wonderful trick when it first came out. And we've now got a way of doing word machine learning. We stuff our words in, and you can imagine that there's hours of lectures on the way this works and all of the little nuances and fiddles that you have to make it work in various domains. But that's the basic principle. Word2vec works beautifully. And of course, once you've got that, you can do all sorts of exciting things. So, for example, you could run a machine learning problem where the input was some information about a restaurant. You say this is a Chipotle Mexican grill and it's on Merriman Parkway in Las Vegas, and please could you output a 5-star review, please? And you could learn all of those, and then you could produce a set of reviews. Here are 4 of them, and I can tell you that one of these reviews is machine generated. So I don't know if you can see them at the back. I'll read them to you. Review 1 is, I have never had a bad experience here. The staff is very nice, the place is clean, and the portions are generous for what you're getting. 2, great, Chipotle is my favourite. This location is beautiful and close to home. Service is always on point and the food is awesome. 3, I love Chipotle. It never fails me when I'm starving. I like the fact they use free-range meat. 4, I was never too impressed by their other locations, but this one is great. They are quick and friendly and their food is always, and sorry, I chopped off the rest. Okay, quick straw poll amongst the physical audience. Who here would vote for, just quickly raise your hand as I say the number. Who thinks the fake review is number 1? Who thinks it's number 2? Who thinks it's number 3? And who thinks it's number 4? I think I saw a slight preference from number 2. 1 is the fake review. Now, there is a slight problem with all of these fake reviews in that you have to muck up the grammar. And you have to do that because computers usually learn the grammar rather well. So they have probably added some grammar obfuscation here to make it look real. So this is always a slight problem. Often the training data is too well written. Well, you're not alone in not being able to spot this fake review, ladies and gentlemen. When these authors, nice Finnish authors down here, did exactly the same thing with a group of users, the users couldn't tell the difference. By the way, an artificial intelligence algorithm trained on these can easily tell the difference between fake and real reviews. There are hidden clues that are easy to spot, but humans find very difficult to spot. So that's really an example of machine learning at work, and it's an example of machine translation. Now, just because I couldn't resist it, there's a little bit of fun. This isn't machine translation, it isn't state-of-the-art, but it is a little bit of amusement. Some enterprising graduates at MIT wrote a text processing system that would produce fake papers. The provost of Gresham College is a chap called Sir Richard Evans, and I've always fancied writing a paper with Sir Richard Evans, so I wrote one. Here it is, towards the deployment of the look-aside buffer, and it's a fake bit of computer science. We all got very angry. For many years, if you're a professor of computer science, you get these very badly written things saying, "Dear Professor, we're extremely honoured to have your work. Would you mind submitting to this crappy conference?" And you submit, and if you're foolish enough to submit, you'll be stiffed for $800 of publication fees. They're fake conferences. So these guys were infuriated by this, and they wrote a fake computer science paper generator. If you fancy writing a computer science paper, just go to SciGen, and you too, ladies and gentlemen, can have your own 6-page paper. It's absolute garbage, but looks like a good paper. Needless to say, they were astonished, having written this paper, when they found it was accepted by a number of irreputable conferences, and to hammer home the point, they decided that they would attend the conference as fake scientists. They dressed up in fake lab boots and gave fake talks that they had written a computer program to generate. Needless to say, as often with these situations, the conference organisers were furious and accused them of malfeasance and fraud and all sorts of other things. This seems to be a very common habit in science. I'm sure you've heard of the SoCal hoax, where a well-known physicist submitted a fake paper to a fake journal and spoofed them. This was all done automatically. Now, okay, the peak of this sort of business at the moment is probably IBM. And I like to pick a sort of little example for each lecture. Last lecture we looked at AlphaGo, which was a Google system, and to spread the love around a bit, I'm going to pick a system from IBM. IBM's artificial intelligence is called Watson. Watson, I think, is really multiple artificial intelligences, and the peak attainment was IBM got Watson to play the American TV game Jeopardy. Now, I need to explain Jeopardy rather quickly. It's a complex game. The idea is that you're given a sort of domain of knowledge and the contest and a clue, which is called a question, but it's really a clue, like a crossword clue. And the contestants are expected to process this clue quickly and to give an answer, and they buzz in to get the answer. So I'm not going to show you the final game. The final game was really boring because Watson absolutely trashed. The two biggest champions ever in the history of a game were completely trashed by Watson. I'm going to show you a practice game. You can tell it's a practice game because there's a cameraman muddling around and doing practice angles. This was between one of the contestants here, one of the creators of Watson, and a journalist from Wired magazine. Okay, and I just picked this because it shows you modern text processing at work.
We start with a single Jeopardy round. Everybody's locked in, loaded. Here's the categories that you will play for this round. Starting off with scene of the crime. Tennis vocabulary, anyone? Laundry detergent, always in fashion. Presidential rhyme time, followed by those animals frighten me. How do you feel right now, Miles?
Feeling really bad. All right, yeah. I feeling strong.
You're feeling strong.
You gotta go into this with a positive outlook, don't you think?
Absolutely. Yeah. There's no other way to do it. No other way to do it.
Yeah.
All right, Miles, you're in our first position.
Right.
If you're ready to go, we're going to start us off.
I am ready. Let's do presidential rhyme time for 200, please.
Here we go. Barack's Andean pack animals. Watson.
What is Obama's llamas?
Obama's llamas.
Oh, boy.
Yes,
Okay.
got it. That's what this category is all about. Barack's Andean pack animals, Obama's llamas. Good for $200, Watson. Go ahead.
400, same category.
Here we go. George W.'s rumps. Watson?
What is Bush's tushes?
Bush's tushes. George W. Bush. Bush's tushes. Yeah. That's how we're going to do this, Miles.
Okay, I get it now. I get it. Thank you, Watson.
Go ahead, Watson.
600, same category.
Yep. Zachary's padded envelopes. Watson.
What is Taylor's mailers?
Zachary Taylor's mailers. That's exactly right. 12th President Zachary Taylor. Go ahead, Watson.
Same category, 800.
800. You're doing well so far. Herbert's strategic military exercises. Watson.
What is Victor's electors?
No. Miles?
What are Hoover's maneuvers?
That is correct. You're on the board with $800.
Okay, well, you now know how Jeopardy works. It's quite hard, isn't it? It's like solving British crossword clues. It's a really impressive bit of language processing, I think. Because remember, they're not all poets that poetic couplets that rhyme with the names of presidents. There's a wide range of knowledge that Watson has to understand. He has to do speech recognition to understand this guy. He has to very quickly process his memory banks and answer all of these questions. And then they insisted a buzzer was pressed. So somebody in IBM had to design a little electromechanical thing that went and press the buzzer and buzz in ahead of the people. And there's also some strategy. There are different points, different prizes on offer, and so on and so on and so on. A very impressive bit of text processing, and I think particularly impressive given that the responses were learnt from previous Jeopardy rounds. So it's very sort of equivalent to you or me sitting there watching Jeopardy and trying to work out how to solve it. So Watson, I don't think was. You never know with these commercial demonstrations how much was sort of hardwired into the device. But the claim is that Watson learnt not only the answers but really the methods for producing the answers. Okay, so that is probably the apex of achievement in current text processing, but I just wanted to draw your attention to a couple of others. It's very common, isn't it, for people to sort of disparage this performance and say, oh, well, of course, a computer could never be creative, When a computer produces a sonnet, I shall hang up my hat. Okay, well, there is a sonnet generator, and various people. This is actually the winner of the Auto Sonnet competition, which runs, I think it runs every year now. And I have to admit that I am not a particular expert on poetry or sonnets, but it sort of looks like a sonnet to me. And I was also slightly entertained by a slightly more sophisticated system, one of the recent prize-winning papers on text processing, where the challenge is to learn from an image a poem. So the way they did this was they got, I think it's about 30,000 image poem pairs together, and they also got, I think, about 100,000 poems just sort of sloshing around. And so they learnt not only what a poem looks like, so it should have, you know, proper meter and so on, but they also learnt the mapping from the image to the poem. It's quite impressive, isn't it? You know, so this one here, the sun rays struck my face, warm tingles to my fingertips. The light showed me a path. Well, there is a path there. I should walk down. I spoke, and whispers of breeze told me to close my eyes. I lost my way in a paradise. So this was again tested. So when you do these problems, you really need to test them against humans. And naive humans cannot tell these poems from the real thing, as my recollection. However, experts can currently tell them from the real thing. So there's an interesting area that has been explored in the sort of final few minutes of this talk, really, which is the connection between these systems that are based on information science, and they're able, well, I've talked about systems that can work with images, I've talked about systems that can work with sound, and we've talked about learning in this series, and today we've talked a little bit about text. The question that comes to mind, I think, is how can this be applied in the fields of creativity? And I'm happy to tell you that that is the final lecture in this series, which takes place on the 20th of May, and we're going to look at whether computers can ever be artistic. Thank you.